be represented by a vector, and I will now write in 2 dimensions. You will see very soon why I am only talking about 2 dimensions. I am sure you all know it. R vector. In polar coordinates, and here also I can write down velocity vector is dx dt I. Acceleration is so. In polar coordinates, there are 2 over a single loop. 2 is R and R cap, which I can write it as if I draw my picture. This value is a vector. This is x I cap y j cap. R cap is cos theta I plus and theta cap is a vector in that direction is minus sin theta I plus. If I keep moving my particle, if a particle is here, x is in this direction, I cap is in this direction, y cap is in that, j cap is in that direction. The direction of I doesn't change. But on the other hand, for r cap, if I move in this direction, r cap direction changes. So if I do that, I can write down dr dt right from here. That is nothing but minus sin theta I plus cos theta j. Which is equal to minus plus theta. Similarly, d theta d cap. If I differentiate this, I get minus cos theta I plus sin theta. I'm doing some things which are quite elementary, which all of you know. It's nothing but minus r. So now, if I write my r vector, position vector again, I'm writing that as r cap, my velocity v, not only have to differentiate r, but r cap also. Notice here, di cap dt is 0. There is direction of I cap, I, j do not change in Cartesian frame, whereas r cap dr dt is non-zero. In fact, it is theta d theta d. So v cap would be r cap plus r theta dot. And a, the acceleration, I have to differentiate this now. I would get r double dot r cap plus r dot theta cap plus r dot theta dot. I am differentiating this now, theta cap plus r theta double dot theta cap. And last, I differentiate the theta, that gives me minus r theta dot square. So when I connect all this, this is of course the standard thing which we all know. This is the centrifugal term, cap, centripetal force, which acceleration, centripetal acceleration plus r dot theta. Now I am ready to write my central force expression. I will assume that I have a particle of mass m here, and this is fixed, and I have another mass m attracted to this by gravitational force. So my force is equal to minus gm by r squared. This is the Newton's law, which is given by m d squared, which is the acceleration. I already have an expression for that. That is m r double dot minus r theta dot squared r cap plus root r dot theta dot plus actually, if I have m not as fixed, it is you have to work with your center of mass, which is the one which will be fixed, and then both m and m will go around in whatever be the orbit. If I assume my m to be very much larger than capital M, for all practical purposes, this will be addressed, and I am working in that approximation. Otherwise, you can do the standard elimination of trying to get to the center of mass. If necessary, we can discuss that in our tutorial. Okay? Now, given this, I get, notice the left hand side has only r cap, here I have r cap and theta cap, so I get 2 r dot theta dot plus r theta double dot. This of course can be written as d dt r squared theta. This left hand side is, apart from the factor of 1 by r, when I differentiate this, I will get 2r r dot theta dot plus r squared theta dot. So this is just see, which means r squared theta dot. This is nothing but the angular momentum of the particle apart from the mass. What is the angular momentum? Let me just magnitude of the angular momentum. Angular momentum vector, you know, is r cross p, and r cross p is nothing but r cross m r dot r cross plus r. The first term is 0, and the next term is nothing but r m r times theta dot times r cross theta. And r cap theta, r is this way, r theta cap is a vector coming out of the black hole, so that is, and magnitude is r, because the angle between r vector and theta vector is 90 degrees, so I get m r squared theta dot times vector out of the black, which I will write out. For a central force, this expression dl dt we all know, I am just writing it. dl dt is dr dt cross p plus r cross dp dt. But dr dt is velocity, and this also is velocity. V cross V is 0, so I get this as r cross f. And F for a central force is along R, so this answer is 0. So this means L is a constant vector. When I mean it's a constant vector, it means its direction also cannot change. So in this particular case, which I have here, the angular momentum is in this direction. So the angular momentum has to be in this direction, which means this particle must be moving in the plane. Because if it tries to get out of the plane, now of course the direction will change, so that's not possible. So this implies particle will remain planar. And what is the magnitude? The magnitude is m r squared theta naught. So that is your absolute. So I write now theta naught is equal to, I will call that J. I will also use another symbol r squared theta naught equals J by m, which is equal to h. Now let's go back to the other equation. The next equation is the r double dot, which is, I will rewrite this thing as dV is equal to this acceleration minus gm. I have cancelled m from both sides. R squared. So from this equation, I can write my r squared as 1 by r squared as minus gm by j by m theta. The algebra that I am doing now is slightly different from the normal textbooks use. This algebra is slightly easier, and I'll just explain the difference. But what is my theta naught now? I have here r theta naught with the minus sign is d theta 2. Right? So I can rewrite this as gn. Is this okay up till now? So I can take it to the other side. I get ddt d minus g by j. That means v minus g is a constant vector. In my notebook, just to be consistent, I have multiplied this by m to make that shape. This is actually related to a vector which goes by the name of Runge-Lenz vector. It is not quite that, apart from some minor changes. This is nothing but the Runge-Lenz vector. It is one of the constants of motion occurring for this 1 over r squared potential. Now, so let me draw my x-axis this way, and let this be the A vector. Let this angle be phi. And let the particle of mass m be making an angle theta. Then this angle is phi minus theta. So if I write A dot r gap from here, that is nothing but A cos phi minus theta will be equal to A cos phi minus theta is m v dot. A dot theta cap would give me v dot theta. A dot theta cap is A sine phi minus theta equal to m v dot theta minus but what is v dot theta? V I already here, so it is r theta. So I can rewrite this as m times r theta. But again I can use this relation r squared theta dot equal to h. Oh, I could have written this in this, or m j by m, since I am using m, I continue doing that. So I get r theta dot is nothing but m into j by m r minus g m by g equal to a dot theta a sine phi. So notice, this is of the form something like 1 by r, and if I take it to that side, some a sine phi minus theta. That is the equation of an ellipse. If the standard equation of an ellipse that we write down is the following, which I will convert this into the standard form. What I will do is I will choose my phi to be 90 degrees. That is, if I take my A vector to be in some direction, 90 degrees to that is my x-axis. Okay? That is, if my A is a constant vector, 90 degrees to that is my x-axis. That's my choice. If I do that, then this becomes pi by 2 minus theta, so I get A cos theta equal to j by m, j by m. Or 1 by r equal to j by j of theta cross g. I will just wait here for a few minutes to see. I have done a lot of straightforward algebra, but just make sure that if there are any questions, the way normally which you will find in books, the derivation of this is that you take the radial part of the equation, and write r equal to 1 by u, and then try to solve for u. You will get a differential equation for u, which is of the form a sine phi cos phi. Then you are able to solve it, which is a little more long. And on the other hand, this particular problem has an extra constant of motion because of the 1 over r squared. I have just used that fact to simplify the algebra. If you look at almost all textbooks, you will know. Slightly different. And I have noticed that when I talk this to students, they find this easier than the other question, because ultimately it gives the same response. Okay, now let me establish a relation between this and the eccentricity of the orbit and so on. This is the equation for ellipse. Now, the satellites and various voyagers that have been sent require these equations. So what I'm going to do is use this equation and apply it to some things which voyagers have done. Let me just explain that. Some simple details. Voyager 1 and Voyager 2 were launched in 1977, and the Voyager 1 went past Jupiter in 1979 and Saturn in 1981. All this you can get from surfing in the net. Right? Voyager 1, Voyager 2, you will see all this. And it passed Uranus in 1986. More recently, there is a Cassini spacecraft which had been sent as a mission to Jupiter. But Jupiter. Okay. This was a joint effort of NASA and European Space Agency, and it was launched in 1997. Then it reached Jupiter around 2003, and then Saturn around 2004. What they did was to get to the Jupiter. Every one of them, they used a method of sending the rocket up to close to a planet. Once you get close to the planet, you use the gravity of the planet to make it move and pick up energy from that and further go down the orbit. What I am going to do is use this example to calculate how one can use the presence of a planet to gain energy and what will be the equations that you will need. So it will be a direct application of what you have learned here, plus the fact that energy is conserved and trying to connect different frames. One frame in which the sun is at rest, in which the planet is moving in an elliptical orbit. Another is a frame in which you go to the planet and see how this Voyager or Cassini move across that planet. So that's the aim. So in order to do that, I need some more expressions connecting the eccentricity of the orbit, which I will get from here. So let me write those equations. So before I proceed, is there any comment, anything that you would like to add, subtract, debate at this stage? Is that
right? When you exploit an intermediate planet and want to continue going, does the orbit remain the same plane throughout in practice?
In practice,
or does it tilt?
Actually, when the planet approaches it, it remains in the plane of the planet plus the object. That is the velocity vector. That part of it, as long as it's in the plane. And once it's out, it will just move in a different direction. That's kind.
Sir,
yes.
Small question, sir. That A constant A, how do
A
you
vector?
explain it, sir?
A vector you are talking
Its
about?
significance, yeah. How do you look upon it? Constant A.
Here, it really comes from some symmetry, extra symmetry.
Yeah, here you can see it is the direction of the semi-major axis. Case of elliptic.
It is a direction of one of the axes of the ellipse, which remains the same.
Yeah, because you have taken phi based on constant A. Phi. Vector phi.
That's right.
Yeah.
So it's in that direction.
Okay. So when you are defining eccentricity, you need to know vector A for that.
Yes, I will use the A expression for A here. Sure. But A is known because the value of A is completely fixed from this expression here. If you give me the value of B at a particular place, I know how A looks. Right? But he is right. It is the direction of the semi-major axis with some value related to energy. Energy and angular motion. Both are constant. Okay, so let me just do that. Thanks. I will write down my expression for this as 1 by r equal to 1 plus e cos theta divided by a into 1 minus. So if I do that, from here I can write down a by j is equal to what is a by j? 1 by a into e square. 1 minus e square. And the other one is g and m squared by g squared equal to 1 by. So from here I can calculate E. I will just keep the algebra, write down the answer. It is A j by m because I know A here and E squared. So all I need to do is substitute and get that expression. It is m squared.
E by raised to P E.
Pardon?
So A by raised to P E. E squared.
The cos theta, coefficient of cos theta term
A by J.
is coefficient of cos theta term is A by J.
A by J.
And on the other side, and here coefficient of cos theta term is E. Oh, this is E. So this is
That's E.
something seems not right here. E is equal to, correct? Then, so okay, it's all right. It's now, just to make sure that this gives me the correct answer, I will just tell you what the standard checks that we can do. We know the thing which people learn in school is 1b squared. So, y squared by b squared. And b squared is a squared into 1 minus b squared plus 1. This is the standard equation of the ellipse that we learn in school. So if I write down that here, I'll just connect this to this so that you know this is the 4f, this is O, and this distance is A. And this whole length is OA. And OB is B, which is A into square root of 1. To connect this, r theta coordinates are about this foci, r theta. So x, if you substitute x equal to AE plus r cos theta and y equal to r sin theta, then from this equation you can go to that equation or the other way around. This is the relation between something which the students know, x squared by a squared plus y squared plus b squared equal to 1, and this is the equation. Okay, so if foci is here, this distance is AE. I am writing all this because I need this to discuss in some detail how the rocket, or the Cassini Voyager, which went across the way. The next thing is I need the following relation relating the energy of the, I'll write down E squared. I'll write the relation and I'll derive this E squared equal to 2 G x squared divided by E. There is my E. E is the energy of the particle. Let me derive this. To derive this, let me write down the, let's call this A and A prime. The energy at A, at this point A, is nothing but the potential energy plus the kinetic energy. The potential energy here is minus gm by this distance, and that is, then OA is A, so FA is A minus AE, which is A into 1. So it is A plus the kinetic energy, which is M, plus kinetic energy is plus half M V squared. At this point, notice it has only, there is no R dot, because the particle is coming with a velocity like this and it is moving, so the velocity is only in that direction and there is no R dot, so it is R theta dot squared, R squared theta dot squared, and R squared at that time is nothing but A squared. This R is nothing but A squared times 1. One minus E. And theta dot squared I can calculate from here. I have it, this expression. So my theta dot squared from there would be, if I substitute for that, I will have J squared by M squared half A. So this expression is minus GMM by A into 1 minus E plus half times M and M cancel. So the J squared by M, R squared, so I get 1 by R squared, so A squared times 1 minus same thing about A prime. This is clear. I have the potential energy plus the kinetic energy. I can do the same thing about this point. So now the distance is 1 plus E, so this becomes minus G M M by A into 1 plus E plus R J squared by M divided by A squared times 1 plus. I can use this equation to determine A. Okay? I can bring this one side and take it. I can determine A. I will again skip the algebra here. I will write down the answer. A is h squared divided by h I had defined somewhere. There it is, J by M, a G M. And if after having obtained this A, if I go ahead and substitute in this instantly, so if I go ahead and substitute this value of A here, I will get so I need this. Dust comes from conservation laws of angular momentum plus energy. Now we are ready to study the motion of the satellite or the Voyager, which is going around the planet. I will draw that here. Let the planet move in, say, let me look at firstly in the planet's rest frame. Let me also tell you the kind of approximations I am going to make. The object, the Cassini, has left the Earth gravitational field. Then its only influence is that of the Sun. Till, yes, please ask.
Here you are, of course, assuming EA is equal to EA prime.
Pardon?
We are assuming EA is the EA prime, right?
EA is equal to EA prime. That I am assuming the energy here, total energy here is the same as total energy. And that can be proved again because gravitational field is a conservative force. So I can write down that in terms of a potential, and that is the potential energy I have written down here. This term is the potential energy. I have not discussed that in detail. This is something which
No, but, I mean, what I was thinking is why we need to say that we can prove it, because that is the assumption, right?
which one?
That energy has to be conserved.
No, that can be derived completely from the following statement. If my
So once we are writing potential energy, it is understood it is conservative potential.
Correct.
Okay, once we do that, after that, it becomes very obvious that EA should be same as
Yes,
EA.
that's correct. That's correct. Absolutely. Look, so long as I am dealing with the conservative force, energy is conserved.
Yeah, once we write potential energy means it is.
That's right. But for the gravitational force, I can write a potential.
Right.
Yeah.
No, because at the end you made a statement. First we have conservation of energy.
No, what I meant, maybe I didn't say it properly.
Yeah.
What I mean is, using conservation of energy and angular momentum, I have this equation. Now, let me go over the approximations that I am going to make for my satellite. The satellite leaves the Earth, and so it is only under the influence of the Sun. So it is going to go into some elliptical orbit, depending upon, or hyperbolic or parabolic orbit, depending upon its original velocity. It will come close to the planet that we are talking about, in this particular case, Jupiter. The Jupiter, moment it comes very close to the Jupiter, I am going to make an approximation. Jupiter is what is going to completely control its motion. So at some stage, it is only Jupiter till it leaves Jupiter. After it has left Jupiter, say at a distance of 20 times the radius of the Jupiter. So again, the influence of the Sun is more important, and that will dominate its motion. So right now, the way I will look at it is, this is my planet Jupiter, and the Cassini is coming with some velocity here, and it will turn around and go. This I will write it. It is coming from infinity. This is in the planet's rest frame, Jupiter's rest frame.